You know, it's funny how the simplest questions can sometimes hide the most profound, most complicated truths. We're about to dive into a puzzle so simple you could explain it to a kid, but so deep it actually challenged the very definition of truth in mathematics. Let's get right into it.
Okay, here's the puzzle. Imagine any map. A map of the world, a fantasy map from a novel, doesn't matter. The only rule is you have to color it so that no two regions that share a border have the same color. So what's the absolute minimum number of colors you'd need to pull this off for any map you can dream up? Seems pretty straightforward, right?
For more than a century, everyone kind of knew the answer was 4. I mean, you can try it yourself. Go ahead. Try and draw a map that actually requires 5 colors. You'll find you can't. But knowing something intuitively and proving it mathematically are two totally different worlds. And proving that 4 is always enough, well, that turned out to be one of the toughest problems in the entire history of math.
And I'm not being dramatic here. The hunt for proof pushed mathematicians to the absolute brink. It forced them to ask some really uncomfortable questions about what a mathematical proof even is. The answer they eventually found would change the game forever.
So, where did this whole thing even come from? The story of the four-color conjecture, as it was called, is a real journey, full of brilliant ideas, frustrating dead ends, and just sheer, stubborn persistence. It all kicked off in 1852, with a student just coloring a map of England. For a few decades, the problem was just kind of floating around, but then it really took off in the math community. And in 1879, a guy named Alfred Kemp published what everyone thought was a rock-solid proof. People celebrated. The case was closed. Or so they thought. 11 years later, another mathematician, Percy Heawood, found a tiny but fatal flaw in the logic. Kemp's proof was completely wrong. The puzzle was back on, and for the next 86 years, it defeated every single person who tried to solve it. So, when the solution finally did arrive, it wasn't the beautiful, elegant pen-and-paper proof that everyone had been dreaming of. Nope, it was something different. Something that made a lot of mathematicians really, really uneasy.
In 1976, two mathematicians at the University of Illinois, Kenneth Appel and Wolfgang Haken, announced to the world that they had done it. They had solved the four-color problem. But how they did it? Well, that's the real story here.
Okay, so you gotta understand what a classical math proof is supposed to be. It's meant to be a product of pure human reason, something elegant that a person can read, follow, and verify for themselves. Appel and Haken's proof was, well, it was none of those things. It was a brute force calculation carried out by a computer. It produced so much data that no single human could ever hope to check it by hand. It wasn't derived from pure theory, what we call a priori. It was more like a scientific result based on running the program and checking the evidence, what we call a posteriori. Get this, their proof required 1,200 hours of computer time. Now you have to remember, this is 1976. That is an absolutely colossal and almost unimaginable amount of processing power for that era. And what was the computer doing for all that time? It was checking 1,482 specific, fundamental map configurations. The strategy was brilliant. They showed that any map, no matter how complex, had to contain one of these configurations. Then, they had the computer check that each and every one of those could be four-colored. It was an idea that's impossible for a human mind to actually carry out.
And this just sent shockwaves through the math world. It created this huge philosophical crisis. I mean, if no human can actually verify the steps of the proof, can we really say we know it's true? Are we trusting logic? Or are we just trusting that a machine ran its code correctly? Is this even math anymore, or did it just become an experimental science? It seems like a classic either-or problem. But is it?
Maybe, just maybe, the problem wasn't with the proof. Maybe the problem was with the rigid, black and white boxes we were trying to shove it into. This situation was screaming for a new way to think, a way to see beyond these simple categories. This quote just nails the issue perfectly. Formal logic, that's our normal either-or thinking, it's like a photograph. It gives you a perfect, crystal clear, but totally frozen snapshot of a moment. But reality isn't a snapshot, is it? It's a motion picture, constantly flowing, full of contradictions and change. And to see the world in motion, you need a different kind of camera.
And that tool, that different way of seeing, is called dialectics. It's a mental model built specifically to handle complexity, to understand contradiction, and to see how things change over time.
Now, you've probably run into this simplified version before, right? Thesis, antithesis, synthesis. An idea comes along, it clashes with its opposite, and out of that conflict, a new, better idea is born. It's a neat little formula, but let's be honest, reality is rarely that tidy.
In fact, the sociologist Jürgen Ritzert famously called this simplistic model a rickety three-step. It's a bit clunky, a bit mechanical. It doesn't really get to the true power of dialectical thinking. To do that, we have to go a little deeper.
So here's the crucial idea. A more sophisticated view of dialectics isn't about two totally separate things clashing like bumper cars. It's about seeing how opposites are actually inside of each other. They're interconnected, they're intertwined. The tension between them is the engine that drives all development and all change forward.
Okay, so let's take this more powerful idea and go back to our map problem. From a dialectical point of view, Apple and Hawkins' work wasn't either a proof or an experiment. The tension between those two ideas created something totally new, a computer-assisted proof. It had parts of both inside of it. It was a synthesis that literally changed our definition of what a proof could be.
This also perfectly shows us another core principle of dialectics, the transformation of quantity into quality. Think about heating water on a stove. You're adding heat, that's a quantitative change, degree by degree, 98, 99. Not much is happening. Then suddenly, at 100 degrees, bam, you get a dramatic qualitative leap. The water becomes steam. It's the same thing with the four-color proof. The massive quantity of calculations, 1,200 hours, nearly 1,500 cases, it reached a tipping point and produced a brand new quality of mathematical certainty.
And the best part is, this way of thinking isn't just for obscure math puzzles. It's an incredibly powerful lens for understanding the world all around us.
Take a look at this. Formal everyday logic would look at these and just put them in separate boxes. They're different, static objects. But dialectics encourages us to see the process. It asks, how does one of these forms become the next one? It sees the connections and the movement, not just the frozen snapshots.
So, why does any of this matter to you? Because thinking this way is a seriously practical tool. It helps us get out of those rigid binary traps, those good versus evil or right versus wrong narratives. In any complex system, politics, society, even our own personal growth, things are rarely so simple. Dialectics gives us a way to understand the nuance, the hidden contradictions, and to see how real change actually happens through tension.
Ultimately, it's about upgrading our mental software. It's a fundamental shift from seeing the world as a collection of static, separate things to seeing it as a dynamic, interconnected process that is constantly unfolding, constantly evolving, constantly becoming something new.
So I'll leave you with this to think about. Look at your own world, your work, your beliefs, your relationships. Where are you stuck in a simple either-or choice that might be hiding a much deeper, more complex, and way more interesting dialectical truth, just waiting for you to find it?